All right. Hello. I've already welcomed everyone who's here already, but also hello to everyone who's watching this on the video. I'm David, I'm the coordinator of the Maths Learning Centre, and this is the revision seminar for Mathematical Economics 1. It's semester 2, 2020, which is why we are here in my house doing this from home over Zoom. Okay, so I've had some requests and we're going to start with some integration stuff. And before we actually talk about that, I would love it if people could tell me how they feel about integration. So you don't have to say it aloud. What I think would be a good thing for you to do would be to, this is like, oh no, and this is like, yay, this integration is awesome and I'm great at it. And if you're able to annotate your screen, could you put a mark somewhere on this line about where you feel about integration? And everyone, if lots of different people do it, I can see how you feel about it. And luckily, no one will be able to see if it's yours. Oh, I will turn off that ability actually. Right. All right, so we've got several people somewhere in the middle going, it's, you know, I'm not like, oh my goodness, awful, but I'm not, this is the best. That's a natural feeling to have about most maths things. Okay, so it sounds like everyone's feeling they could be a bit better with this. And that's a good place to start. So Jared has very helpfully, feel free to keep marking it while I talk. Jared has very helpfully and Caitlin have helpfully given me a couple of problems that involve integration, and I'm going to do them. They're ones that I think your lecturer has given somewhere along the road, but don't have solutions. So I'm going to do those. Thank you everyone for engaging with that very small task. I'm going to clear them all and start talking about it. So I'm going to launch into doing some examples and we can talk about the details later as we are going on. So actually, do you know what? I just need to talk about some things. I need to know a couple of things about the techniques you've been taught for doing integration. So if you could please, because I'm not part of your course, I don't know what you've been taught. If you've got any names of techniques of integration, could you type them in the chat? So one I know is substitution, because it looks like from this example, you're going to have to be able to do that. But are there any other techniques, named techniques that you've been given? By parts, cool. And substitution, they're the main ones. I'm interested in a particular one, and we'll get to that soon. Were you taught about partial fractions? Does that phrase sound familiar? No? Okay, cool, good to know. Awesome. So, and there's going to be a couple of other secret techniques that your lecturer has done and that you can do that he hasn't. It is a he, isn't it? Jiaping. He hasn't named. So I'm just going to talk about that for a second. So when I think about how to integrate, I think about there being several different techniques. And there are, in my opinion, I don't know how many there are, but I'm going to start. Technique 0 is to just do it. If you already know the answer, just let me fix my, there we go. If you already know how to do an integral, if it's a power, for example, power of x, then you can just do it. If it's e to the x, you can just do it. There's a list of things that you know the derivative of, and therefore you know the integral of them. 1 over x. All of these things you can just do without having to do any special work. Under the just do it category, I also include anything that has a linear thing inside it. You know, familiar function with like ax plus b inside it. And I'll talk about that when I get up to it. Okay, so that's just do it. Then technique number 1 is to rewrite it in a different form. So maybe you'll expand out some brackets, expand out some multiplications or powers that have got brackets around them, or maybe factorize things, cancel some things from the top and bottom of a fraction. Those sorts of things can make it easier to do the integral, because what will happen is you'll take something that looks complicated, you'll rewrite it in one of these formats. And then number 2 is substitution, which is an extremely fancy way of rewriting things that involves not just rewriting the part that's going to get integrated, but also rewriting the bit with the dx or the d whatever. And then number 3 is by parts. Okay. And I would in general recommend trying them in these order. And that by parts is sort of a bit of a last resort for specialized situations. That's my advice for general techniques of integration. Yeah, and what I'm going to do is, knowing that that's my list, I'm going to work on the examples that I've been given. Right. Let's have a look at this now. What was it? This. Okay. So currently it's thing to the power of -1, which is a power of x, but it's a very special power of x. The one with the -1 is different, and most people would rewrite it like this first. So now it looks like 1 over x, but instead of an x, it's got something linear, because it's -1x plus 6. So I know how to do something like that, but the first thing I'm going to do before I do any of this is to just check to see if this function even makes sense at these places. So if x is 2, I'll get 1 over 4, which is perfectly well defined. If x is -1, I'll get 1 over 7. And so this thing will range from 4 to 7. So it's never going to be 0. So I'm going to be allowed to do this integral. That's going to be perfectly fine. If this function was undefined, somewhere in between here and here, then it wouldn't even be possible to do this integral. And I just need to check that first. Okay. So I would know what to do if this was just an x. If that was just an x, I would get ln of thing. Or does your lecturer call that log? Can someone confirm that, whether your lecturer calls this ln or log? Okay, cool, that's fine. Some people pronounce it ln. I pronounce it ln, like the daytime chat show host. So that's ln, and it should be ln of x minus 6, except if I differentiated this, I would have to multiply by the derivative of this, which would give me a minus 1. So I'm going to have to divide by that -1 like that. And this trick of dividing by the derivative of the thing that would be in the position where you'd normally hope there'd be an x, that trick will only work if the derivative of that inside thing is a constant. It only works if it's linear. And then I have to sub in the 2 and the -1 and subtract them. So that's minus ln of 6 minus x. Technically, it's supposed to be ln of the absolute value of 6 minus x, because that might come out as negative. So I'm going to get minus ln of 6 minus 1, and then minus ln of 6 minus 2. And so I've got minus ln of 7 plus ln of 4. I don't know what format your lecturer prefers here, but it might feel better if it's just the ln of a single number. I'm not sure. Ln of something minus ln of something else turns it into division on the inside. Ln of 4/7. Okay, whatever that is. It's a negative number though. I don't know if he wants an approximate one, but I'm going to look it up anyway. Just need a calculator. Actually, I've got a calculator. I don't need to use my phone. (0.5596). All right, so how are people feeling about what just happened? Cool. If anyone is not feeling thumbs up about it, feel free to say, or to circle something on the screen with the annotation tool that you're not sure about and that you'd like me to talk more about. Okay, awesome. All right. So this is my first thing, and that thing there where you divide by the derivative of the linear thing that's inside, it's a very useful trick, and it makes a lot of integrals a lot faster. Okay, let me try this one. I'm not doing them in the order that I was given. I'm just doing them in the order that I can think to do. Okay, so this one here, it's an indefinite integral, so I'm going to get a formula rather than a number at the end. I'm going to run through my list. I don't already know how to do this. It's got a couple of things multiplied together. That's a bit complicated for me. So I'm not going to be able to just do it, but I might be able to rewrite it, because if I expand it out, then it's going to be a combination of a couple of powers of x. So I reckon what I'm going to do is I'm going to rewrite this as x to the minus 2 times x to the 4, which is x squared, and then x to the power of minus 2 times 5, like that. And then now it's written in terms of stuff that I know how to do. I know how to deal with an x squared because it's a power of x. I know how to deal with an x minus 2, it's a power of x as well. And the 5 being multiplied on will still be there. So x squared will go up to x cubed, and I'll divide by the new power. The 5 is multiplied on, so it'll still be there afterwards. X to the power of -2 will go up to -1, and I'll divide by the new exponent. And because this is an indefinite integral, that's the formula I want, but I have to cover all the possibilities, so I'll whack a plus c on there. And then that's 1/3 of x cubed. Now that minus will make that a -5. The x to the power of -1 will end up on the bottom. I don't know what format your lecturer prefers, but this is nice. I'm happy with that one. So how do people feel about that one? All right, thank you. Okay, so this was my technique number 1 of rewrite it. And there are plenty of situations in which expanding out a multiplication will make it possible to do. There are some where it won't. It'll just be just as hard as it was before, but it's a good start. Okay, let me try this one. This one looks less fun, if I'm honest. I definitely don't know how to do it already. Yeah. And I am wondering if there is a specific list of things that you are supposed to already know how to integrate that this looks like for you. I could be wrong. Yeah, I'm just going to run through the techniques I happen to know for dealing with this. I mean, normally I would attempt to factorize the bottom and hope that it cancelled out with something on the top. Yeah. Except just let me check if it's even possible to do this one. When x is -1, this answer is 3 times -1 squared minus 1, which is 3 minus 1, which is 2. And when x is 0, this is negative. So, okay. So between x equals -1 and x equals 0, 3x squared minus 1 3x squared minus 1 is between 3 times -1 squared is 3 is 2 and -1. And so denominator is 0 somewhere in between in the interval from somewhere from x equals 0 to x equals -1. Well, -1 to 0. So this function doesn't actually exist in every place that we're trying to do the integral, so the integral doesn't exist. At some point in the interval, and therefore the integral from -1 to 0 of x cubed minus 1 over 3x squared minus 1 dx doesn't actually exist. That's what I think. The exact place where this would be 0 would be at like the cube root of 1 on 3. Sorry, the square root of 1 on 3. And at the square root of 1 on 3, the top's not 0. So yeah, this function thoroughly doesn't exist somewhere in the interval. And so the integral itself doesn't exist. How do people feel about that? People are feeling less comfortable with that. So feel free to ask a question about that. It's okay. Someone's saying they hadn't seen something like that before. Yeah, I mean, it's a bit of a double bluff to say compute the following integral and for the answer to be it's not possible. Can I again show how it's undefined? Sure. So I could do it a different way if you prefer. I'll do a different way and then I'll redo what I just did. Should we attempt integrating anyway if the function doesn't exist, just in case? Well, as far as I know, you haven't been given techniques that will integrate this function. And your lecturer has deliberately done that. Yeah. So if it didn't have these numbers here, then you could definitely you should definitely attempt to integrate it, because you might be integrating in a place where it does exist. So you could, thinking that your lecturer hadn't realized it wasn't defined, make an attempt to at least find an indefinite integral. That would be my only advice if you had some extra time in an exam. However, I don't think you've been taught techniques to solve this one. So I'm just going to go back to Tashisha's one question of how do you show it was undefined. So this will be, I'm going to give it a name, f of x, 3x minus 1 is undefined when the denominator is 0. And the denominator is 0 when x is plus or minus 1 on root 3. And minus 1 on root 3 is between minus 1 and 0. All right, and so since minus 0.55, no, we don't. We want to use the exact answer, don't we? Since minus 1 on root 3 is between minus 1 and 0, f of x is undefined at a point in the interval from minus 1 to 0. How do you feel about that? So my argument before was that I don't actually need to solve the actual equation to know where it's undefined. I just have to know that it's technically possible for this to come out to 0 somewhere in this interval. And so what I did is I calculated it at x equals minus 1, which is what and I got the answer 2. And I calculated at x equals 0 and I got the answer minus 1. So somewhere between here and here, this denominator must come out to 0 because it goes from positive to negative. And that's how I knew that it had to have a place where it was undefined. I just didn't actually find the place where it was undefined. I knew it had to be there. So it was a way of me avoiding having to actually solve the equation. I'm just going to think just a little longer about this. So if it had been without the minus 1 there, and these two numbers had been different, I reckon I might have been able to actually do it. So I could be wrong, but I could give it a go. I like to try and do problems, but I reckon this version of the problem can't be done. Yeah, I mean, yeah, I am wondering about what if it had been just this. So this is now a made-up question. Made-up question. Let me see how I go at it. So I can't currently rewrite it. Doesn't look likely. But I could attempt substitution. I mean, the rewriting, yeah, I mean, there's no way for me to divide this by that. I could do polynomial division and end up with, yeah. I'm still not going to be able to do it, I think, but I'm going to give it a go. I'm going to call it substitution and let this be u and see what I get. And then du on dx would be 3 still there times 2x, that's a 0, so that's 6x. Now, I don't know how your lecturer does this. There's lots of ways to do substitution, but this is how I do it. I go looking for things involving the dx. So I can see in my formula there's an x dx as part of that x cubed there. So that x dx can be replaced with a 1/6 of du. And this is u, so that leaves me to deal with that x squared. And so from this, oh, we can do it. How cool is that? No, we can't. Damn it. Sorry. Maybe not. I'm getting ahead of myself. So u plus 1 is 3x squared. No, we can't. We wouldn't have been able to do it at all. So a third of u plus 1 is what x squared is. And so now I'm able to replace the x squared. And so therefore, my integral will be the x squared is a third of u plus 1. The bottom is u. And this is a 1/6 of du. I think I've done all the pieces right. The 1/6 of du is the x dx. This is u, and that was a third of u plus 1, yep. And now it's an integral that I have to try and do not with substitution because I've already used substitution. So that third and that 1/6 can multiply together to make a 12th. And then when I'm thinking about that, I could actually divide this by u and I'll have a 1 plus 1 on u. And that I can integrate because the 12th is multiplied on, so it'll still be there. The integral of 1 is u. The integral of 1 on u is ln, the absolute value of u. And then I can have a plus c. And then u is really 3x squared minus 1. Yay. So that one actually was possible using substitution. If there had been a minus 1 at this spot, I reckon I might, no, I wouldn't have been able to do it because I wouldn't have been able to separate out this x dx. Yeah, so everything would have been yucky if there had been a minus 1 there. How do people feel about what I just did? Oh, sorry. Could it work as an indefinite integral if the x cubed plus 1 were u instead? Okay, let's give it a go. So are you talking about this original one here? So you're saying, what if the u was equal to x cubed minus 1? And then the du on dx would be 3x squared, and du would be 3x squared dx. Now, there's a problem. There's nowhere that there's a 3x squared multiplied by a dx anywhere. I can't arrange that to be in this without changing all of this to be different stuff. So that's my problem. So I could try and whack a 3x squared in there, and then there'd be a 3x squared on the bottom, but then the bottom would be just awful. So yeah. Sometimes it takes a little bit of scribbling on paper to be sure that you can't do it. In general, it's not a good idea to do u equals of the top line if the bottom line has a smaller power. Yeah. Of course, if it had been without the -1 there, I would have divided both parts by this, and I'd be able to do it by rewriting the integral a different way. This is one of the things that I do when I'm studying to help me make sense of things. I go, sure, I don't know how to do this problem, but if I changed it in these ways, could I know how to do it then? And it gives me lots of practice at doing integrals or whatever it is that I'm working on, because I keep making up new problems for myself. Okay. So there's one more integral that I've been given by people, and I'm going to give it a go now. I don't know what number I'm up to. I think it's 5. The integral of x e to the x squared plus 1 dx. So I could attempt to rewrite it if I wanted. I guess I could do e to the power of x times e if with that, but I don't know if that's going to be any better. Certainly can't bring any of this down here. That x attached to this is rather annoying. So my first guess, so I'm not going to be able to rewrite it in any useful way, I don't think. If this had just been an x plus 1, and that x hadn't been there, I would have been able to just do it because I would divide by the 1 there that's next to the x. The squared is really bothering me. So the only thing I can think of is to call this u. And then du on dx is 2x. And I do have an x dx, but I don't know that 2, so I'll just move it out of the way. Okay. So that deals with the x dx, and that's a u. Okay, so everything's done now. So my integral of x e to the x squared plus 1 dx. The x dx is a half of du, and the x squared plus 1 is u. And so a half is multiplied on, so it will still be there afterwards. E to the power of u, the integral is e to the power of u, that doesn't change. And then there'll be a plus c because this is an indefinite integral. And then e to the power of u is really e to the x squared plus 1, because that's what u is. How do people feel about that substitution? Okay, so good question. Is it possible to do this by parts? Well, let's give it a go. I don't think it is, but I wouldn't mind trying. So if I was going to do this one by parts, then by parts is specially designed for when there's two functions that are multiplied by each other. And you have to integrate one of them and differentiate the other one. I don't know how to integrate this one all by itself, so I'm going to have to differentiate that one. I don't know how your lecturer runs integration by parts and what sort of notation that he writes, but this is how I write it. If you want to tell me that that's different to what he does, that's fine, and I can try and match his notation. But I would normally say that this is two things multiplied by each other. And doesn't really matter what letters I use. And then when I do the answer, it will come out to this instead. And just one of these has a dash here, like a derivative dash, and the other one has a derivative here. So if this one was v dashed, I'd have to integrate it to find out what v is. So I don't want to do that. I want to do it this way. So that I can say that the u dashed is x, which means that the integral of u dashed would be a half of x squared. And then the v is e to the x squared plus 1. And so the v dashed would be e to the x squared plus 1, because that's how they don't change. And I'd have to times by the derivative of this, so 2x. And so my integral would become u, which is a half of x squared, times v, which is e to the x squared plus 1, minus u, which is still a half of x squared, times v dashed, which is 2x e to the x squared plus 1. And that's worse. Got an x cubed now. And so this function that I still have to integrate, I mean, this bit's fine, but this still has to be integrated. And now it's an x cubed, not an x. It's getting worse. So I don't think integration by parts is going to help. And my usual rule is to try substitution before I try by parts, in the hope that it will help. Yeah, I don't necessarily try it properly. It's sort of fiddle in my head and go, do I think the power is going to get worse? Do I think this thing looks almost like the derivative of that thing, in which case substitution is going to do it. So integration by parts would have worked very well if that had not been an x squared and had just been an x. Because if that had been not an x squared, then this derivative would just have been that. And in fact, I wouldn't have even chosen this u and v if it had been the integral of x e to the x plus 1 dx. Then I would have said, okay, so I'm going to have to differentiate one, integrate the other. Whether I integrate or differentiate this one, it'll be exactly the same as it was before. Integrating this will make the power go up, which will be worse, but differentiating it will make the power go down, which would be better. And so I would go, I would put the dash here, like that, so that the u is x, and then the u dashed becomes 1, and the v is dashed is e to the x plus 1. And so the integral of that would be still e to the x plus 1, but I'd have to divide by the derivative of that inside, which is just 1 anyway. And so I'd get u is x, v is e to the x plus 1 minus u dashed, which is 1, times v, which is e to the x plus 1. And so I'd have x e to the x plus 1, and then the integral of e to the x plus 1 is still e to the x plus 1. That's how I do that one by parts. My decision of which one had the dash was based on which one would turn into something closer to being constant when I differentiated it. So yeah. How are people feeling about integration? If they've got any other problems that you'd be interested in me having a go at, then let me know, or any other questions about integration at all. Cool. Before I finish off with that, would someone like to say something that they learned just then, or something that it made them feel differently about? Just so that we can close off and think actually something useful happened there for me. Yeah. All right, all good. Okay. Well, let me just have a look at my other lists of things that people have asked about. And I'll see what I can do next. So if you don't mind, Jared, I'm not going to do the thing with the sign diagram because I did that last year. And we've only got half an hour to go. So I'd like to do one of the other things. Let me just check something. Okay. So I can see that, okay. Thanks, Alina. And thanks, Jared, for putting a little read up writing the function. That is good. Okay. So I can see a few requests about things to do with induction and sequences and stuff. So I'm going to do one of those. So I've got a question here that goes, show by induction that the sum of the first n+1 natural numbers is Sn+1, which is n+1 times n+2 over 2. Okay, so induction requires you to, well, let me just talk about that. So induction is the gold standard of how to prove things about natural numbers. So when Peano in the 1600s sat down to think about how to create mathematical foundations of arithmetic, he said he managed to prove that you could get all of everything you might want to know about numbers, starting with just there is 0 and every number has a number after it, and the principle of induction. And that is enough, takes forever, but that is enough to prove anything that you want if you start there. And so that's why induction is such an important tool, because it's historical. Yeah. So induction allows you to prove something if you can think of a way of turning one statement into the next statement. True for n equals k. And you chuck that into some sort of fabulous machine and it spits out true for n equals k plus 1. Then what will happen is you can feed this in here and it'll tell you it's true for the next number, and feed this in here and true for the next number. And if you have a number like 4, so it's true for n equals 4, blip, 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 true for n equals 5. And you can sub that back in here and it'll work, and now it's true for n equals 6, and it'll just keep running forever, and it'll be true for everything from 5 onwards if you've started at 5. So as long as you have a place to start, and this machine then the process of induction will prove that it's true for everything after your starting point. And if you want it to be true for all the natural numbers, then you just need to make sure that you start with the beginning of the natural numbers when you do this. Pardon me. So what I need is a way of turning the statement that the sum of the first k plus 1 natural numbers is this into the statement that the sum of the first k plus 1 natural numbers is this. And that means I need to think about how to turn the sum of the first k plus 1 natural numbers into the sum of the next one. So that's what I'm going to think about. So suppose the first k plus 1 natural numbers is and then I have to include some sort of working here, and then go, therefore, the sum of the first k plus 1 natural numbers is s k plus 1, which is k plus 1 k plus 1 plus 2 over 2. I have deliberately not simplified these because I want it to be about the number k plus 1. So I've subbed it in without expanding it out. But we know that this is k plus 2, and this is k plus 2, and this is k plus 3. Okay, so I would like to conclude with this statement, and it's a statement that two things are equal. And so one way of proving that two things are equal is to start with one of them, do working, and end with the other. I don't know if I have enough space in this spot to do it, but I'm going to give it a go. So let's see. So consider the sum of the first k plus 2 natural numbers, which is sk plus 2, which would be 1 plus all the way up to k plus 1, then k plus 2. And this bit here would be s of k plus 1 because it's the sum of the first k plus 1 natural numbers. And according to the supposition I have here, that is the same as this. And my goal is to make this equal to that now. So I guess they've both got a k plus 2 in them. So I could factorize that out. K plus 1 over 2 plus 1. And I don't like this. That's bad. Maybe I'll factorize out the half as well. And that will leave me with k plus 1 plus 2. And that is k plus 1 plus 1, k plus 1 plus 2 all over 2. And so therefore, it's done. Well, the whole proof isn't done. This part of the proof is done, the machine. And all I need to do now is to be sure that the statement it's true for n equals, I guess, 0 maybe, is true first. So let's just see what happens when n is 0. So sum of the first 0 plus 1 natural numbers is S1, which is just 1, because I haven't, I just added up all of the first one natural number, which is just 1. Okay. And 1 plus 1, 1 plus 2, no, 0 plus 1, 0 plus 2 divided by 2 is 1 times 2 divided by 2, which is 1. And so therefore S0 plus 1 is 0 plus 1, 0 plus 2 over 2. So it is true when, so true for n equals 0, and therefore true for all n greater than or equal to 0 by induction. So how do people feel about what I did there? Can't fit it all on the screen at once, I'm sorry. Feel free to say anything. I'm assuming that people are okay. That's not usually a good assumption when people are silent. But not being able to see your faces, I can't tell how you feel about it without you saying something. But I'm going to move on if people are okay with me moving on. So feel free to stick a thumbs up if you're okay with me moving on to something else. Thanks. Okay. I will just say different styles of induction require different sorts of reasoning in this gap here, but I find it one of the easiest ways to set it up to have a supposed thing, finished thing, and know that I'm going to have to fill in the bit in the middle. Okay. Just going to have a check of this email. Okay. So I've got a question here that I'm going to share with you. It's a counting combinatorics question. And then I might even have time for one of these other things as well, but I'm going to do that first. Okay, so it goes how many ways can you choose 12 donuts from 20 different types assuming there's at least 12 of each type? And you are allowed to have multiple donuts of any type, you know. Oh, wow. Okay. Now I'm going to be flying blind here. I don't know what your lecturer has taught you about how to do this, but I have ways of doing it. So the first step for me to figure out a counting problem is to know what sort of object we are counting. So as far as I can tell, we are counting collections of 12 donuts. And I need to know what makes those collections of 12 donuts different from each other. So if I have like type 1 and type, they could all be type 1. That's one collection of donuts I could have. And I could have, you know, 1, 2, 3, 4. I could have all of them type 1 and then one type 2. And they'd be different. And I could have all of them type 1 and then one type 3, they'd be different. Or you could have like several 1s and several 2s and several 3s. Okay, so it seems to me that what it is that makes them similar or different to each other is how many of type 1 there are and how many of type 2 there are and how many of type 3 there are. So a collection of 12 donuts will be distinguished by how many of each type of donut there is. Okay, cool. So what I need is a way of creating a story that will produce all the different lists of numbers of different kinds of donuts. That's what I'm going to need. So I have a way of telling that story as a story. Your lecturer probably has a different way. I'm not sure. So I'm going to tell mine and then I'll see how yours turns out. So if I was describing to someone how to go to the donut shop and get the collection of 12 donuts that I want, I could give them a list of how many of each one. And if that person, that's one thing I could do. And that person could be standing at the desk, standing at the bench at the donut shop, and they could work their way along. There'd be like all these 20 bins of trays of donuts. And then what they'd do is they'd say, they could work their way along the trays and say to the person serving them, yeah, I want one of them. I don't want any of those. I want one of them, and another one of those, please, and another one of those, and another one of those. Yep, that's cool. And none of them, and none of them, and another one of those. And they could work their way along and create the list of donuts that way by either telling the person who's serving them to move to the next tray or to give them another donut from the tray they're currently up to. And so that's what we can do. So it could also be a list of instructions that goes made of another donut, please. And next type of donut, please. Okay, so I'm going to say that a D and a T. And so there's going to be overall, you're going to have to move through all the trays. You're going to start at tray 1, so there's 19 trays to move through. So there will be 19 T's, and they're going to have to get 12 donuts by the end. So they're going to have to ask for donut 12 times and 12 D's. And so we're going to have a list of 19 T's and 12 D's in some order. And so out of the total of 31 different instructions, 12 of them have to be D's. So 31 instructions, choose 12 D's. And so the number of ways is 31, choose 12. How does your lecturer write this? I write it with this symbol, but some people write it like this. The C one. Okay, so that's what your lecturer does. Cool. All right, so that's my description. That's my story of how I create such a thing. The other story is that many mathematicians and economists and various other people like that go all the way back to this position in the story back here. Oh, I haven't replaced my paper properly, I'm sorry. They go all the way back to this position of the story, and they say, you know, let x1 be the number of the first type of donuts, and x2 be the number of the second type, blah, blah, blah. x20 is the number of the third type. And so we need x1 plus x2 plus all the way up to x20 to be 12 donuts total. And they recognize that this situation always comes out with one less than the number of variables, plus what the answer is supposed to be, choose the answer, which is what I did. So there's 20 variables, and result 12. And so therefore the number of ways is going to be 19 plus 12, choose 12. And they just remember that a situation that has this sort of equation produces this answer. I want to know how people are feeling about that, especially Elaine, who asked the question. Yeah. So you have to trust that this produces the correct answer. And the reason it produces the correct answer is that it's the same story. You can actually, when you start out with them all being 0, the answer will be 0. And every time you add 1 to these, it'll make the answer go up by 1. And so you need to add 1 12 times. And you can do it one piece at a time and go, well, do I want to add 1 to this? Yes or no? And then if you don't want to, you move on to the next one, and you might add 1 to this 6 times, and then you move on to the next one, you might add 1 to that. And so there's a list of instructions that says move to the next variable or add 1 to the variable I'm up to. And that list of instructions has to have 19 move to the next variable and 12 add a 1. Whereas some people describe it as saying, well, there's a whole lot of, each of these can be thought of as made of a whole lot, several plus 1s, or several 1s. and then there's 19 plus signs. And if there's nothing in between them, there's nothing in 0 in that variable. And so there's a list of 19 pluses and 12 ones, and you have to choose out of that list of 31 objects, 12 of them to be ones and 19 to be pluses. So that's another way of thinking about it. Yeah. So it's one of the more complicated counting situations. Yeah. My way of getting there is to remind myself, how do I tell if they're different? I tell if they're different by how many of each object there is, and that gets me very quickly to this equation if I want to go that way. All right. Well, maybe one more thing, and I'll try and choose it from my first list of things. That's not that one. Okay. So I've got one that was from, I think, a practice exam or something. It says you've got f of x is ln of 2x plus 3, and g of x is e to the power of x. And it says, what's the domain of definition? What are the derivatives? Limits at the boundaries of the domain. And 4 inverse functions. So the domain of definition, as far as I'm aware, is the collection of all the x's, if their variable is x, collection of all the x's for which it's possible to calculate these functions. So I know that e to the power of x is always defined no matter what x is. So g of x is equal to e to the x has domain the entire of the real numbers. And that's true for e to the power of anything. I could put anything in this spot. Well, anything that, like a polynomial in this spot, and e to the whatever would always be defined. So the next question is, what about f? Well, ln is only defined when this thing is strictly positive. So to be defined, we need 2x plus 3 to be properly greater than 0. It's not allowed to be equal to 0 because you can't do ln of 0. It can't be negative because you can't do ln of a negative number. And so I'll need 2x to be greater than minus 3 and x to be greater than minus 3 over 2. So the domain is from minus 3 on 2 up to infinity. How do people feel about that? Feel free to use a thumbs up if it's fine, or ask a question. Does your lecturer use this notation? The interval notation? Yes, they do. They must, because there's a question on here that says things in interval notation. Cool. I'm all good. Okay. That's a round bracket here, not a square bracket, meaning the minus 3 on 2 isn't actually included in this domain because it's not defined there. Okay, so I need some derivatives now. 2. The derivative of ln of 2x plus 3 will be 1 over 2x plus 3. because that's the derivative of ln. Because of the chain rule, I have to multiply by the derivative of this, which is 2. So that'll be 2 over 2x plus 3. And g of x is equal to e to the x, and the derivative of e to the x is e to the x, because that is the multiples of e to the x are the only functions that do that. All right, let me do the limits at the boundaries of the domain. Okay, so the boundaries of the domain for e to the x, the boundaries of the domain would be plus infinity and minus infinity. So the limit of e to the x as x goes to plus infinity is infinity. I don't know if your lecturer allows you to write equals infinity or not for a limit, do they? Okay. Go check. If you're not allowed to write that, then you have to say sort of g of x goes to infinity as x goes to infinity. Those are two alternative ways of saying the same thing. Some people don't allow this. Yeah. Okay, and the limit as x goes to minus infinity of e to the x. Well, e to the power of a negative number is 1 over e to the power of something. So if I go e to the power of an extremely large negative number, that would be 1 over e to the power of a very large thing. And so that's going to be 0. So e to the negative very large number is extremely close to 0. Okay. The limit as x goes to plus infinity of ln of 2x plus 3 is also infinity. Ln is a properly increasing function, and it doesn't produce, it doesn't level off to a limit. So as this goes to infinity, ln will go to infinity as well. And the limit as x goes to minus 2/3, because that's the other end of the domain, because it was here. So minus 3/2, sorry, not 2/3. Well, that will mean that this number will go to 0, and ln of 0 doesn't exist. Ln of 0 is negative infinity. So this function starts existing at minus 3 on 2. It goes to minus infinity there. It eventually goes up to infinity there. That's this function. How are we feeling about what happened there? Cool. And then we got one thing left, is to find the inverses. Your lecturer's tendency to use the word characterize, I think, is hilarious, because I've never known anyone other than the people who run this course to call it characterize. All other maths people would call it find. So I just think it's just cute and weird. But I think when they mean characterize, they mean give a formula for. Okay, well, I know how to do the inverse of e to the power of x. The inverse of e to the power of x is ln x, because that is the definition of e to the power of x and ln x. They are inverses of each other. So I'm allowed to just do that. F of x is going to be a little different. So I could, there are two ways of going about this. I could think, well, what does f of x do to x? X, I times by 2, and that produces 2x. And then I add 3, and that produces 2x plus 3. And then I do ln, and that produces ln of 2x plus 3. And so the inverse would go backwards. So it would do this thing backwards, which would be e to the power of. So the inverse would begin at x and do everything backwards. So do e to the power of, and that would be e to the power of x. And then it would do -3, and that would be e to the power of x -3. And then it would do divide by 2, and so, because that's the opposite, and I'd have e to the power of x -3 divided by 2. And so therefore f inverse of x would be e to the power of x -3 over 2. That's one way. The other way, it's going to fit in this space here, would be to say, well, let y be f of inverse of x. And then I know if I did f on both sides, that would mean that f of y was x, which would mean that ln of 2y plus 3 would be x. And then to get rid of an ln, I should do e to the power of. And then to get rid of a +3, I should do -3. And then to get rid of a times 2, I should do divide by 2. And since y is f inverse of x must be e to the power of x -3 over 2. Which one of these do people prefer the most? And which one is most like what the lecturer did? Let me call this A and this one B. Which one do you prefer the most? The right? Yeah. Cool, thank you. This is the one I find easiest to process on paper. This one's hard to read, but some people find this one easier. But I think the lecturer would probably like this one best. Yeah. I like beginning with let y equals thing I'm trying to find and then doing working. I find that nice. So the only other thing that the lecturer asked in this question was make sure you specify the values of x for which each of these functions exists. So the output here, I know the values of x for ln. This is just 0 to infinity because that's when ln is defined. We already discovered that ln of 2x plus 3 produces everything from -infinity to +infinity. And so therefore the inverse should take in everything from +infinity to -infinity. So x is anything in R, which makes sense because I'm doing e to the power of x and I'm allowed to do that no matter what x is. I'm going to have to stop there because I have another revision seminar coming soon and I need to have a little break, like for a different course. But I want to say to you, Maths Learning Centre is open, both face-to-face and online today and on Monday and on Tuesday too, though we won't help anyone during your actual exam. I'm just looking up when, I'm not allowed to tell you when your exam is, but yeah. So we're not allowed to help you during your actual exam, but you can drop in both online and face-to-face any time we're open between 10 a.m. and 4 p.m. up until that point. So feel free to ask any of your other questions of any of the staff there and we'll help you out. Thanks for coming. I hope that was helpful to you. Last thing to do before you sign off for the day is to think to yourself, what was something there that was really useful for me? And if you want to let everyone else know that's in the chat, that's great, but otherwise you can know it in yourself. The recording will be uploaded onto the Maths Learning Centre's YouTube channel, and I will put it on your special resources page and I'll email you all when it's done. Good luck, everyone. I wish you clear thinking and calm nerves for your exam. And yeah, don't forget to keep asking questions. Thanks, everyone.